For this lecture, we're going to continue our discussion of functional groups, specifically alcohols and carboxylic acids. And then we'll talk about some important reactions that occur with regards to these functional groups. So we'll do an overview of alcohols, including the acidity of the hydroxy group hydrogen, as well as hydrogen bonding. We'll talk about redox reactions involving alcohols. Then we'll discuss the SN1 and SN2 reactions, which are not specific to alcohols, but they fit into this lecture. We'll also talk about the protection of alcohols, specifically using methylates and tosylates. And then we'll do a brief overview of carboxylic acids. We'll talk about nucleophilic attack reactions involving carboxylic acids. And then we'll talk about forming a few carboxylic acid derivatives. And we'll talk about redox as well as decarboxylation reactions of these acids. And finally, we'll talk about halogenation and substitution at the alpha carbon of carboxylic acids. So alcohols have a hydroxyl group, which is an OH group, bound to carbon. An alcohol group in a molecule may be indicated by the prefix hydroxy or the suffix -ol, OL. Molecules that have alcohols have intermolecular hydrogen bonding. So oxygen has two lone pairs. Each lone pair can act as a hydrogen bond acceptor. And then, so that's two hydrogen bond acceptors for the oxygen of the alcohol. And then the hydrogen of the alcohol is a hydrogen bond donor. So that intermolecular hydrogen bonding makes alcohols have strong intermolecular forces and therefore high boiling points, etc. So alcohols are generally weakly acidic. The pKa is pretty high, between 15 and 20 in general. Alcohols that have more alkyl groups nearby the hydroxyl group are going to be weaker acids. And that's because those alkyl groups are electron-donating groups. So the resultant conjugate base, which forms when the hydrogen of the hydroxy group is deprotonated, and so this oxygen is going to be left with a negative charge. And that conjugate base is going to be destabilized if there are multiple alkyl groups nearby, which are going to be electron generous, so donating electrons towards an already electron-dense atom. An atom with a negative charge already harbors more electrons than preferred. One exception to this general pKa range is the phenols. Phenols are actually more acidic than most alcohols. That's because the negative charge of the conjugate base is going to be delocalized by resonance of the aromatic ring. So if I recall correctly, phenols have a pKa around 10, so the phenol alcohol is a little more acidic than other alcohols. This is a primary alcohol, so the carbon is attached to one other alkyl group, and this is a secondary alcohol, so the carbon's attached to two other alkyl groups, and then of course a tertiary would be attached to three other alkyl groups, so this hydrogen would be another R or alkyl group. So redox reactions involving alcohols. We talked about this a little bit last lecture when we discussed aldehydes and ketones, but we'll review it again. So if you're looking at the oxidation state of carbon, the most oxidized carbon is the carbon in carboxylic acid. The least oxidized is an alcohol. And in the middle you have carbonyls. So alcohols can be oxidized to aldehydes or ketones, which can be further oxidized to carboxylic acids. Alcohols can also be directly oxidized to carboxylic acids. So they're going to be skipping a step, which is going to require a strong oxidizing agent. So you see here, this is just an example of increasing the oxidation state on the carbon, going from an alcohol to here specifically an aldehyde, and then finally a carboxylic acid. So if you have a primary alcohol, so that's an alcohol whose carbon is attached to one other R group, so this would actually be an H. You just have one R group on the carbon. And you add a weak oxidizing agent, you'll get an aldehyde. So if you replace this R1 with an H, so you have an H here and then an H there, then you'll get an aldehyde. If you have a secondary alcohol here, and you add any oxidizing agent, weak or strong, you'll get a ketone. So these two depict going from an alcohol to a carbonyl, aldehyde or ketone. If you have a primary alcohol and you add a strong oxidizing agent, you skip completely the carbonyl group step, and you go from an alcohol all the way to a carboxylic acid. And so that requires a strong oxidizing agent to go from an alcohol to a carboxylic acid, which is depicted here. And that needs to be a primary alcohol. So you might be confused why primary alcohol plus weak. Why only weak? Well, because if you're adding strong, it's going to be a carboxylic acid. If you're adding weak, then it'll become an aldehyde. And then finally, if you have a tertiary alcohol and you add an oxidizing agent, there's no reaction. So what is a strong or weak oxidizing agent? Well, specifically the ones that you should know. Essentially, if it's not one of these strong oxidizing agents, you can assume it's a weak oxidizing agent. So some ones that are especially strong oxidizing agents are salts or acids of these compounds, which are transition metals with oxygen. So MnO4-, Cr2O7-, CrO4-2. And some weak oxidizing agents are PCC, which is shown here, PDC, which is shown here, and DMP. So if you see these abbreviated terms, which represent weak oxidizing agents, then they're some of the most commonly used weak oxidizing agents in the lab. But these ones are especially strong oxidizing agents. And what is categorized as a strong versus a weak oxidizing agent may fluctuate a little bit. So even online, some things have PDC in the strong oxidizing agents category, and some lists don't. So it is not a really cut and dry kind of thing, but as long as you know in general that a weak oxidizing agent plus primary alcohol goes to an aldehyde, whereas a strong oxidizing agent plus a primary alcohol goes to a carboxylic acid, then you're understanding the underlying principle behind the oxidation of alcohols, which is the most important part. So next let's talk about SN1 and SN2 reactions, which are particularly important for the MCAT. And all of the things that I list here, some of the key characteristics of SN1 reactions, I would try to commit to memory, also try and of course understand the basics behind it, but these things do come up, and it's something that I remember was pretty new to me because I had taken organic chemistry a while ago. But once you relearn SN1 and SN2, they become pretty intuitive, and as long as you understand the reaction, then all of the other characteristics that are part of the reaction make sense. So SN1, that stands for unimolecular nucleophilic substitution reaction. So 1 is for unimolecular and nucleophilic, S for substitution. Unimolecular, if you remember back from our discussion of kinetics, unimolecular refers to a reaction rate that's only dependent on one species. So the overall mechanism of an SN1 reaction, you have a carbon bound to a leaving group. A leaving group first leaves the molecule, and then you form a carbocation. So that carbocation is not just a transition state, it actually forms and exists in solution. When you form that carbocation, that's sitting in solution, and that then gets attacked by a nucleophile that's also sitting in solution, and it can be attacked on either side. We'll talk about the planarity of this carbocation in a second. And then you form your product. So there are two different products that can form depending on which side the nucleophile attacks from. So here I've just kind of simplified it. You have carbon bound to a leaving group leaves, and you have a carbocation intermediate. And then the nucleophile attacks that carbocation, and you have R bound to the nucleophile. So it's a substitution. You substitute out the leaving group for the incoming nucleophile. The rate is unimolecular, and it only depends on the concentration of the electrophile, which is this guy here. The carbon bound to the leaving group. So rate is equal to K, rate constant, times electrophile. And what this tells you is that the rate of the SN1 reaction depends only on the molecule with the leaving group here. And that's because the mechanism's slowest step, or the rate determining step of this two-step mechanism, is this first step in which the leaving group leaves the molecule, forming the carbocation. So remember, a carbocation is unstable. So the leaving group leaving and forming this carbocation is the rate determining step because it's particularly slow. The nucleophile attacking and forming the product is really a rapid step. So remember, complex reactions which have more than one elementary step, if there's a rate determining step, then the rate of the overall reaction is just equal to the rate of the rate determining step. And the rate of the rate determining step here is just the rate constant K times concentration of reactants. And the only reactant we have in the rate determining step is that electrophile, or that alkyl group bound to a leaving group. So you see here it says slow for the leaving group leaving and fast for the nucleophilic attack step. So you form a carbocation intermediate, and that carbocation has carbon bound to 3 other atoms. So it has planar geometry and 120-degree bond angles. Why is that important? Well, that's important because that carbon, so it has planar geometry with its 3 attached groups, and it can be attacked from the nucleophile on both sides of the plane. That means that both the R and S forms of the product are made. So what you make is a racemic mixture, which remember is a combination, a 1-to-1 ratio of the enantiomers. So you form equal amounts of the R and S forms of the product. That's why here you see 2 products forming. One is R and one is S. And the nucleophile you see can attack from either side. Something else to note is that the carbocation can rearrange via a hydride shift if there's a more stable carbocation possible. Remember that more substituted carbocations, such as a tertiary, is more stable than a secondary. So those surrounding alkyl groups of a tertiary carbocation are electron donating and decrease the effect of the positive charge on the carbon. So if the adjacent carbon is more substituted and would therefore be a more stable carbocation, then the positive charge can shift via the shift of a hydrogen atom. So you see here the leaving group, X, leaves, and you would have a positive charge on this carbon here. But that can shift, and you can also, via a hydride shift, have the positive charge here or here. That means the nucleophile can either attack this carbon or this carbon. And that means that actually 4 products are possible. The R and S of this guy and the R and S of this guy. The stability of the carbocation that forms determines how quickly the reaction occurs. Because remember, forming the carbocation is the rate determining step. So how quickly that reaction proceeds is dependent wholly on the rate determining step. And the rate of that rate determining step depends entirely on how stable that carbocation is, as well as how good of a leaving group it is. But really we can think about it as the stability of the carbocation being the prevailing factor. A more stable carbocation, such as a tertiary carbocation, is going to form more rapidly. It's going to be a quicker rate of the reaction. So under what conditions are SN1 reactions preferred over SN2? Because SN1 and SN2 have the same basic reactant to product conversion. You have a leaving group leave and exchanged for a nucleophile. But why would SN1 occur instead of SN2? Well, under specific conditions, and that's what we're going to discuss. If the carbocation that you form from the leaving group leaving is tertiary, SN1 is always preferred over SN2. If the carbocation that you form from the leaving group leaving is methyl or primary, so methyl being, it'd be CH3 plus 1, primary being RCH2 plus 1, then SN2 is going to occur because that carbocation is so unstable that it's not going to be able to form via an SN1 mechanism. So if tertiary carbocation, SN1, if methyl or primary, SN2, if secondary, either SN1 or SN2 will occur. So if you are going to form a secondary carbocation, or basically the carbon bound to the leaving group is a secondary carbon, then a weaker nucleophile would actually favor SN1 over SN2. So these are examples of weaker nucleophiles. And you'll see that stronger nucleophiles are halides. So a weaker nucleophile would favor SN1 over SN2 if you're in this, I don't know whether it's SN1 or SN2, which is when you have a secondary carbon, right? And then also, if you have a polar and protic solvent, protic meaning it can donate a hydrogen, those solvents are going to favor SN1. And that's because they stabilize the carbocation that forms in the SN1 mechanism. So here are some images to help you see what's going on. This one specifically is the SN1 mechanism. So here you have the S enantiomer, and here our leaving group is chlorine. Chlorine leaves, forming a tertiary carbocation, which is the most stable. Remember, tertiary carbocation, SN1, always preferred over SN2. So if you looked at this guy and you wanted to know, does SN1 or SN2 occur? You would know right off the bat that it's SN1 because you're forming a tertiary carbocation. So then you have a planar carbocation intermediate, and the nucleophile here can attack from either side. If the nucleophile attacks from the left, then you get the R enantiomer, and if it attacks from the right, then you get the S enantiomer. So you're creating a racemic mixture here. If you see here, this energy diagram is just showing that a methyl carbocation is extremely difficult to form. It's high energy, unstable, and therefore difficult to form. Whereas a tertiary carbocation is much more stable than methyl, primary, or secondary, and is therefore easy to form. It has a lower activation energy. And then here, this is showing, so remember I said if tertiary carbocation, always SN1, if methyl or primary, always SN2, and if secondary, SN1 or SN2. This is, of course, a big simplification, but it's a simplification that I knew and that I learned for the MCAT. So I think it'll almost always hold true, and always did in my experience. But this diagram here is just showing that as you go from a methyl to a tertiary carbocation, the SN1 becomes the predominant reaction, right? Because it's faster. Whereas the SN2 becomes less favorable. So it's sort of inverse relationship as you go from, so when you're at a methyl or even a primary carbocation, SN2 is preferred because it's the faster reaction. Whereas when you're at a tertiary, generally, almost always actually, SN1 is preferred. And then if you're at a secondary, then it could be SN1 or SN2, and that's going to depend on the strength of the nucleophile and whether the solvent is polar and protic or not. Okay, now let's talk about the SN2 reaction. SN2 stands for bimolecular nucleophilic substitution, and it's bimolecular because the reaction rate of this mechanism depends on two species, not just one. Overall, the SN2 mechanism is a single step. Now that is different from SN1. So SN1 occurred in two steps. First you form the carbocation, and then the second step is the nucleophilic attack. So you see here, step 1 and then step 2. SN2 is a single step mechanism. You do have a transition state here, so this is representing the transition state, but this transition state is not an intermediate. So the carbocation here is an intermediate, meaning it actually exists in the solution as a carbocation. So it's not a transition state, which is an extremely transient species that is not considered an intermediate. So what happens in the SN2 reaction is that the nucleophile attacks the carbon at the same time as the leaving group leaves the molecule. So you can think of them as occurring sort of at the same time. And you have a pentavalent carbon as the transition state. So you see the bond between the carbon and the nucleophile is forming as the bond between the carbon and the leaving group is breaking. There is no carbocation intermediate as opposed to SN1. And you end up with the nucleophile bound to the carbon and the leaving group left on its own. The rate of an SN2 is equal to the rate constant times the electrophile, which is this guy, concentration of the electrophile times concentration of the nucleophile. So it depends on both species here. And you see this is a single-step mechanism, and we know that all single-step mechanisms, or elementary reactions, have a rate that's just equal to K times concentration of the products raised to the stoichiometric coefficient. And because this is a 1-to-1 reaction, meaning one nucleophile for one R leaving group, then there's no exponent here. So the carbon is attacked from the backside by the nucleophile. It's referred to as a backside attack. What we mean by backside, it's on the opposite face of the carbon than the leaving group is. And that results in an inversion of the configuration at that carbon from the reactant to the products. So if the reactant is R, the product is going to be S. And if the reactant is S, the product is going to be R. So you only form one enantiomer, whereas in SN1, you formed two enantiomers. But here we have two important terms, backside attack, that's what the nucleophile does to the electrophilic carbon, and you have an inversion of the configuration. The rate of this reaction depends on how sterically hindered that carbon atom is. So how easy is it for the nucleophile to come in and attack it? A methyl carbon, so a carbon that's just bound to 3 hydrogens and would be bound to a leaving group here. So methyl isn't really the most accurate term, but if it's just bound to 3 hydrogens and the leaving group, that's going to be the most quick, the most rapid reaction for SN2. Whereas tertiary, meaning the carbon will be bound to 3 alkyl groups and the leaving group, that would be so slow that it wouldn't occur via SN2. We know that tertiary always occurs via SN1, and methyl and primary always occur via SN2. As I said, the nucleophile attacks essentially at the same time as the leaving group leaves, and you have a pentavalent transition state. But this transition state really should be in brackets with the double dagger, showing that it's not an intermediate, but instead it's a transition state. But this is just a diagram showing the backside attack. So let's talk about conditions that favor SN2 over SN1. So this first bullet here, I want to make a clarification. We know that there is no carbocation formed in SN2, but if you can imagine one forming from the leaving group leaving, then that carbocation, if it's methyl or primary, meaning the carbon is bound to a leaving group and either 3 other hydrogens or 2 hydrogens and 1 alkyl group, then SN2 will occur, because the carbocation that would form if SN1 occurred is far too unstable. So no carbocation can form, meaning SN2 occurs. If that theoretical carbocation is tertiary, we know that that's SN1. And then if it's secondary, meaning the carbon is bound to a leaving group and two other alkyl groups, then it depends on whether it's SN1 or SN2, and it mainly depends on the strength of the leaving group and the solvent. It's favored by polar, or I should say, or non-polar, but in general, aprotic solvents. So aprotic solvents are ones that don't donate a hydrogen, so essentially can't hydrogen bond. And that's just because a polar protic solvent would favor SN1. So if it's aprotic, polar or non-polar really, then SN2 would be preferred. It's also favored by a good leaving group, because the leaving group needs to leave as the nucleophile attacks, so a good leaving group favors SN2. And it's also favored by a strong and small nucleophile. So a small nucleophile is really able to attack that carbon with minimal steric hindrance. So a more bulky nucleophile would have trouble coming in and attacking that carbon, which is bound to 4 other groups already. Commonly, a strong and small nucleophile, which favors SN2, are the halides. So let's look at this reactant here. It's carbon bound to 3 hydrogens and bromine as the leaving group. Is it possible for SN1 to occur? Well, if the leaving group leaves, then we're left with a methyl carbocation. This is an extremely, extremely unfavorable carbocation, and it really doesn't form, meaning SN1 with this reactant is not going to occur. Rather, it's going to be SN2, where no carbocation forms. Instead, there's just a pentavalent intermediate. So this is just an overview of what we've talked about. SN1 or SN2 is a common question that you might be asked in the context of a passage or freestanding on the MCAT. First, you want to look at the carbon. If it's tertiary, meaning 3 alkyl groups are attached to it, as well as the leaving group, then you're going to have SN1. If it's methyl or primary, it's going to be SN2. If it's secondary, you want to look at the solvent, the strength of the nucleophile, and how good of a leaving group it is. This kind of covers what we've spoken about, but this talks about SN1 and SN2 reaction coordinates. So first thing I want to point out, you see that the SN1 has 2 humps. Why? That's because it's a 2-step mechanism. You form the carbocation, which is an intermediate, and then you have the second step of the nucleophile attacking. Whereas SN2 is just a single hump, because you have a transition state, of course, but you don't have an intermediate, so it's just a single step. Here you see that a polar solvent, the red curve, is really going to favor SN1, and specifically polar protic solvents, because those are going to be able to stabilize the carbocation intermediate. So you see a lower energy carbocation intermediate when it's in a polar solvent. And also to note is that the energy of the products is not changed by the polar versus non-polar solvent. So let's talk about protection of alcohols. Well, in general, not just for alcohols, but we often want to protect our functional groups from reacting. And you do that by adding a protecting group. So a protecting group in general is a group that's added to a reactant molecule through a covalent linkage in order to protect a certain region of that reactant molecule from reacting. So what I mean by that is look at this example here in which we have the protection of a ketone. So LiAlH4 we know is a very strong reducing agent. If we added LiAlH4 to this molecule here, it would reduce not only the carboxyl group to an alcohol, but it would also reduce the carbonyl, the ketone, to an alcohol. And in this mechanism, we only want to reduce the carboxyl group. So we want to protect that ketone from being reduced. So the way that that's done is adding this protecting group here. So this group here is going to be added on to that carbon of the carbonyl using a catalytic amount of acid. Then you can react it with LiAlH4, reducing the carboxyl group, which we want to do. Then you can remove the protecting group and regenerate the ketone. So we prevented the ketone from reacting here by protecting it using this as the protecting group. So we often do this for alcohols as well. That's because alcohols can be protonated, deprotonated, substituted, eliminated, and oxidized. And so in order to prevent those things from happening to an alcohol, you often want to add a protecting group to the oxygen of the hydroxyl group, then remove it at the end of the reaction so that you regenerate the alcohol at the end, so the alcohol comes out unchanged. Methylates and tosylates are commonly used as protecting groups for alcohols. They also often protect amines. Something that is important about methylates and tosylates is that they're good leaving groups too. So you need that protecting group to be able to leave once the reaction has happened. So these, you see, have extensive resonance stabilization. So when they have to leave the molecule and gain a negative charge, they're more stable, and so they're okay to leave, which is really favorable for a protecting group to be able to quite easily leave the molecule once the reaction is done. So methylates are often abbreviated OM, M being the methyl group bound to the oxygen it's protecting, and then tosylates often abbreviated OT. So here you actually see if this was an alcohol, so this was OH, the H got removed, and then the tosyl group bound to that oxygen of the hydroxyl group, that's a tosylate. So methylates and tosylates don't react with oxidizing agents that would normally oxidize alcohols to carbonyls or even to carboxyl groups. So how do you prepare methylates and tosylates? Well, a tosylate is, as you can see here, the tosyl group bound to the oxygen that it's protecting, the oxygen of the alcohol. So you add an alcohol plus tosyl chloride, which is tosyl with a positive charge, tosyl group, plus chloride with a negative charge, chlorine. That's a salt, and when this alcohol is deprotonated and this tosyl group comes in and bonds to the alcohol, then you have a tosylate. And the same is done for methylate. You add alcohol plus methyl chloride, that's salt, and you generate a methylate with the oxygen of the alcohol bound to the methyl group from this salt. So essentially the methyl or tosyl groups bond with chlorine in that ionic salt there, gets replaced by bonding the methyl or tosyl group with the oxygen of the alcohol. So now let's move on to carboxylic acids. So I'm sure you guys are aware carboxylic acids are compounds that have the carboxyl functional group, has a carbonyl and an alcohol. And they're often abbreviated by the suffix oic acid, such as propanoic acid, butanoic acid, etc. Because they have a carbonyl, which has an oxygen that can accept 2 hydrogen bonds, and they have an OH, so they have oxygen in the alcohol as the hydrogen bond acceptors, and then the hydrogen of the alcohol as a hydrogen bond donor, they have extensive hydrogen bonding. And that results in strong intermolecular forces for compounds that are composed of carboxylic acids. And then that affects properties such as boiling point. And they're polar and protic. So the bond, the carbonyl bond in the carboxylic acid, so that carbon there, is bound to 2 oxygens, which are very electronegative. And so that carbon of the carboxyl group is quite delta positive, whereas the oxygens are delta negative. So that's quite a polar bond. And so it's a polar functional group, and it's protic, meaning it can donate a hydrogen or protonate other species. Carboxylic acids, as the name indicates, are weakly acidic. When I say weakly acidic, they're not a strong acid, so they're not hydrochloric acid, right? But still, they're stronger acids than alcohols, for example. the pKa of carboxylic acids is generally around 4. If you remember, we talked about the carboxyl group of the amino acid backbone, and we said that pKa was pretty low. So they are acidic. One of the reasons for that, one of the primary reasons, is the stability of the conjugate base. So the conjugate base, COO-, is stabilized by resonance, which I've shown here. Here are the two resonance contributors. And that resonance stabilizes the conjugate base, making it a stronger acid. The strength of compounds with carboxyl groups depends on what atoms or groups are present in the rest of the molecule. So their inductive effects, resonance, etc. And we'll talk a little more about that in the next lecture when we talk about carboxylic acid derivatives. So let's talk about nucleophilic attack reactions that occur with carboxylic acids. So the carbon of the carboxyl group, as I discussed, is delta positive, and therefore it's electrophilic, meaning that it's susceptible to nucleophilic attack. A nucleophilic substitution reaction is a substitution reaction, so one group is substituted for another group, and it occurs via nucleophilic attack. So in a nucleophilic substitution reaction, the alcohol of the carboxyl group is going to become protonated, generally by a strong acid, which acts as a catalyst. Then that alcohol can be a good leaving group. And so a substitution reaction can occur whereby that protonated OH group leaves, and the nucleophile comes in and attacks that electrophilic carbon. So here you see Cl- is going to act as a nucleophile, and it's going to attack that carbon here, and that OH is going to be the leaving group. So carboxylic acids can be involved in nucleophilic attack reactions as the electrophile, so being attacked at that electrophilic carbon. But they can also act as a nucleophile and engage in nucleophilic attack themselves. The pi bond of that carbonyl or the oxygen and the alcohol can act as a nucleophile. So that's shown here in this mechanism where the oxygen of that of the hydroxyl group of the carboxylic acid attacks this carbon here. And then you can also see here the pi bond is attacking this guy here. So in nucleophilic attack reactions, most commonly you'll see the carbon, which is very electrophilic, being attacked by a nucleophile, but be aware that the pi bond or the oxygen and the alcohol can also act as a nucleophile and engage in nucleophilic attack. Oh, just to mention, these are just some examples that I found to show the carboxyl group acting as a nucleophile, but they're not ones that you need to memorize in any case. So there are a number of carboxylic acid derivatives, and we'll talk about how those are formed from carboxylic acids. Specifically, we'll talk about amides, esters, and acid anhydrides, and then the whole next lecture will be dedicated to those carboxylic acid derivatives. But for now, we'll talk about how they're formed from carboxylic acids. So this is an amide. So you see you're replacing the hydroxyl group of the carboxylic acid with an amine. And you can either replace it with a primary amine or a secondary amine or a tertiary amine. So here's a tertiary amide. If these were two H groups, it would be a primary amide and so on. Lactams are cyclic amides, and sometimes you're just given the name lactam without being shown the structure. So it is important to know what a lactam is, be able to recognize it. And so now let's talk about how amides are formed from carboxylic acids. They can also be formed from carboxylic acid derivatives, and they're formed generally by reacting either a carboxylic acid or a carboxylic acid derivative with an amine. So here you see a carboxylic acid reacting with a primary amine, and with the removal of water, so this is a condensation reaction, we get a secondary amide. So it's bound to two R groups, so this is a secondary amide. which you get from reacting a primary amine with a carboxylic acid. Here, what you see is a carboxylic acid derivative, so this X could be chlorine, for example. It could be some other atom that is not OH, that's not a hydroxyl group. But reacting that with a secondary amine, what you end up with is a tertiary amide. So the hydrogen leaves as well as this X is a leaving group. And then finally, here's just a specific example, ethanoic acid, so a carboxylic acid, reacting with ammonia, and what you get is a primary amide. So it's bound to just one alkyl group. And you see that you have to remove this OH as well as one of the H's of the amine, and that's why water is removed. So these are condensation reactions if you're reacting it with a carboxylic acid, as opposed to a carboxylic acid derivative. So esters are essentially carboxylic acid derivatives, but instead of a hydroxyl group, they have some OR group here. Lactones are cyclic esters, which you should know. And how are esters formed? Well, specifically, the formation of esters is called esterification. So esterification is when you react an acid and an alcohol together and you produce an ester and water. So another condensation reaction whereby water is removed from that molecule. So esterification is especially applicable to bio and biochemistry because this reaction is involved in making triglycerides, also called triacylglycerides. Triacylglycerides have ester bonds between the glycerol group and the fatty acid. So if you react a glycerol, which is the backbone of the fatty acid and has 3 alcohols, with 3 fatty acid chains, which are hydrocarbon chains with carboxylic acids, then what you'll get is 3 ester bonds in the triglyceride. So in general, the esterification reaction is a carboxylic acid plus an alcohol gives you an ester, and I neglected to include the water, but that's also included. And it requires acid catalysis, so that's an important point. The mechanism specifically is an addition-elimination reaction. And I've included the mechanism on the next slide here, so you can look at that at your own leisure. I wouldn't say that you have to memorize this mechanism by any means, but just look at it and make sure you sort of understand what's going on. And you can also see why acid catalysis is required at a number of steps here. But in general, I've outlined some of the major steps of this mechanism. The carbonyl is protonated of the carboxylic acid. The oxygen of the ROH group, the alcohol, acts as a nucleophile and attacks the carbonyl carbon. The OH is protonated by the acid catalyst, making it a better leaving group. The hydrogen of the ROH group leaves. The OH group of the original carboxylic acid is protonated, making it a better leaving group again, and leaves as water. And then another deprotonation ends the mechanism. So you can follow along these steps here with this diagram and just see what's going on. But in general, you should just know that esterification is forming an ester by reacting a carboxylic acid with an alcohol and the removal of water, and that it requires acid catalysis. So you can see here, this OH group is removed, as well as the H of the alcohol, and this oxygen bound to an alkyl group replaces that OH group. So next we'll talk about acid anhydrides, which are another carboxylic acid derivative. So acid anhydrides look like this. They're formed from the addition of 2 carboxylic acids, and again, the removal of water, so another condensation reaction. Anhydride, that term, means without water. So acid anhydride is 2 carboxylic acids that are formed with the removal of water. So you see here we have 2 carboxylic acids. One of the OHs and one of the H's are removed. So H2O is removed, and you form an acid anhydride. So this delta, this triangle above the arrow, indicates that heat is added, and minus H2O indicates that water is removed, or water is a product here. So although generally acid anhydrides are formed by reacting 2 carboxylic acids together, you can also form acid anhydrides by reacting other carboxylic acid derivatives. So here you see a carboxylic acid derivative where we have chlorine instead of a hydroxyl group. And then here we have a carboxylic acid salt. So reacting those together, we get an acid anhydride, and we get the salt, sodium chloride. So carboxylic acids can be reduced and also decarboxylated. So remember that carboxylic acids, that's the most oxidized form of carbon, and it can be reduced all the way back to a primary alcohol by using a strong reducing agent. Specifically, we always talk about LiAlH4 as our poster child of strong reducing agents. And so 2 hydrides from the LiAlH4 are added to the carbon of the carboxylic acid, turning it into a primary alcohol. So remember, we could oxidize a primary alcohol into a carboxylic acid using a strong oxidizing agent, and we can reduce a carboxylic acid back into a primary alcohol using a strong reducing agent. Decarboxylation refers to the removal of a carboxyl group, which makes sense given the term decarboxylation. So here you see we're removing this carboxyl group as CO2. This decarboxylation as a reaction commonly occurs for beta-keto acids, which are carboxylic acids that have a ketone on the beta carbon. So remember, this is the alpha carbon of the carboxylic acid. This is the beta carbon. This is a beta-keto acid. And you'll commonly see that decarboxylation occurs for these guys. But decarboxylation occurs for other molecules as well, and it becomes important in biochemistry. So we'll talk about decarboxylation in some of the metabolism mechanisms. For example, the citric acid cycle has a number of instances of decarboxylation. And just note that when decarboxylation does occur, what's lost is CO2 rather than COOH. Finally, we'll talk about reactions that occur at the alpha carbon of carboxylic acids. So if you recall, the alpha carbon is the carbon next door to the carbon of the carboxyl group. And alpha substitution occurs when another atom that comes in from an electrophile replaces the hydrogen atom at the alpha carbon. Just one thing to note, that there is an enol or enolate intermediate as a part of the reaction mechanism. So one example of alpha substitution at the substitution of the alpha carbon is halogenation of carboxylic acids. Specifically, the reaction is referred to as the Helmholtz-Zielinski reaction. And in this reaction, a halogen replaces one of the hydrogens on the alpha carbon. So here's the carboxyl group, here's the alpha carbon. So this hydrogen is going to be replaced by another atom which comes from an electrophile. So comparing this to this, we have alpha substitution. And if this X is a halogen, then that's halogenation of the carboxylic acid at the alpha carbon. So for this specific reaction, some important steps in the mechanism which I've shown on the next page. First, the carboxyl group is converted into an acid halide. So you see, before we can replace that alpha hydrogen, what has to happen is we create an acid halide. So if X is a halogen here, so for example PCl3, that X is going to attack the carbonyl carbon and we're going to get an acid halide here, which is another type of carboxylic acid derivative. After that, an alpha hydrogen is removed and tautomerization occurs. So you see here this alpha hydrogen on the alpha carbon is removed, and we have tautomerization. So here going from the keto to the enol form. And then the halogen is going to be attacked by the pi bond of the enol form. And finally, the halogen is going to be added to the alpha carbon. And the acid halide, also called an acyl halide, is converted back into a carboxylic acid. So what we have here is an acid halide, acyl halide. We convert that back to a carboxylic acid in the last step. So this is also not a mechanism that you need to memorize, but just know that substitutions often occur at the alpha carbon of carboxylic acids, and one specific and common instance of that is halogenation at the alpha carbon. Okay, so that's it for this lecture, and in the next lecture we'll talk in depth about carboxylic acid derivatives, so carrying on from a lot of this content.